And we got a lot to talk about today. Um, Waves. Probably some of you know I'm an acoustician by trade. So the fact that I can't spend the entire semester talking about waves with you makes me feel kind of stifled. But we'll get most of it done, I guess. Enough to talk about. There's two aspects of waves I want to talk about today that are advanced, I guess. And that is Fourier's theorem that talks about using waves to create other periodic structure functions. Okay. And, I'll show you a couple examples of that if those words I just said didn't make any sense. But we've talked about constructive and destructive interference, and we've always added up waves that were exactly the same amplitude. What happens when we start adding up waves that aren't exactly the same amplitude? Figuring out what that amplitude is key. And then we don't always have them be the same frequency either. We have them be perhaps harmonics of each other. Well, according to Fourier, we can create any other waveform we want that is periodic out of that combination. And so we want to show that. And there's a reason, obviously, that if I don't make clear today, Monday when we start talking about uncertainty principle, over that will be clear. And then the other thing I want to talk about, once we make these other structures out of just traveling waves, I want to, we lost somebody. I want to talk about, back again. I want to talk about the difference between the speed of a traveling wave and the speed of some kind of wave that we might turn into a packet. And that's the difference between phase velocity and group velocity. But let's start with just the basics. So I'm going to do a little bit of polling here. I got about 12 quick questions. I just want to whip through them, make sure everybody knows basics of a traveling wave before we start talking about the more advanced stuff. So where is polling? There it is. I'm going to go to waves 1, and I'm going to start sharing my PowerPoint screen with you, which is not where I want it to be. In order, we'll go right to there, and I should be able to launch the poll. And I expect 8 out of 8 here, and everybody should be right. What is the distance between the ends of the blue arrow there? Yeah, I know this is sort of an easy question. Almost an insulting question. Yep, you got it. It's the wavelength. Good. Let's move on. Sorry I had to ask that. Stop sharing. And we'll keep going. A couple of these will get a little harder, I think. What do we call that thing? I've used the word already today, presuming that everybody knew what I was talking about. All right, never gets any easier than this. So share results. All 80, you got it. Good. Let's go on to the next one. Wait, doesn't that look like the first one? Yeah, there we go. Attention to detail and observation here. Check out that. I think you can change your answer if you want. Maybe a change. All right, you're hanging out. Now, I'm sorry for 3 of you, and I don't know who you are, but if it's time here, then that distance in time over which the wave repeats is called a period. Okay. I will say this. Some people call it a temporal period. I've even heard people call it a temporal wavelength, although not as much. But you go the other way. Some people will call the wavelength a spatial period, time and space. See, waves, as you should know, move both through time and through space. Okay. They physically move in maybe the x direction, but they also elapse, they also occur over time. And we talked about Galilean and Lorentz transformations early on. And so that is where the waves live, in both time and space, period here. Stop sharing, move on. 4 and 4. And I'm referring to that sign right there. If it's moving to the right, which way is it going? Or which sign would you pick if it's going to the right? All right, most of you got it. And I don't have a good mathematical proof for this. Truthful with you, it is minus. The only thing I'll tell you is if I had like a parabola located right there at the origin, and so that's something like y is equal to x squared, and I wanted to move that parabola that way, which is what I'm saying. If this thing's going to move, I'm saying I'm going to move it this way, right? Well, what would I do? Well, I think this guy right here would look like y is equal to x minus, I don't know, maybe this is moved to some point a, x minus a squared, wouldn't it? And so this point right here at x equal to a would be the I don't know, what do you call it, the minimum point of the parabola. And it's moved that way by subtracting off that constant a. Well, what we're really doing here, if you think about it, I guess, this is k times the quantity x minus vt. And the speed of this wave times the time, that's equivalent to my shifting by some amount a. And so if I move to the right, it's because I'm shifting by that amount of time interval times the velocity. Okay, not a firm mathematical proof. There's a lot of waving my hands around as I did that, as opposed to some ironclad proof. My other best way to show this is I've got an animation. If you need to see it move, and I can literally change the formula in the animation from a plus sign to a minus sign, and you can watch it go right or left. But that is the answer. All right, stop sharing that. We'll move on. Any questions on that? It's just something you learn, I guess, at some point. And I'll go to the next one. Hopefully that matches. 5, 5, yes. Yeah, so now we're just matching words to symbols, I guess. And I'm looking at in the transverse direction here, right? What do we call it when it's the furthest it can get away from y equals 0, which is right here? All right, everybody's in. Share the results. Yeah, it's that symbol right there. That corresponds to that location in the wave. And I guess minus a would be right there, and plus a would be right there. That's when it's the furthest away. It's the amplitude. That's what amplitude is. All right, stop sharing that. Kind of an odd way to ask the question, I admit it, but it just kind of makes you think a little. And pick a point. I don't know, that one right there. How long does it take for it to go up and down through a full cycle? We lose somebody here? Yep, there we go. Everybody's in. And of course, you got it. Maybe I'd think about it for a second, but yeah, that's a full period, right? That's what a period means. This guy right here goes up, right? As the wave moves that way, and then it starts to come down. It was all the way negative and comes right back up. Now, that's what it would look like if I was running along with the wave at exactly the speed it would look like. I would see that point. Actually, as the wave's going by me, I would see a point go up and down like that. And it would take one period to do it. All right. Share the results. Yeah, I guess I can stop sharing. You all got it. Go to 7 now. Sure I don't lose my place. 7, launch it. Almost the same question. Just the other way, I guess. All right. Yeah, wavelength. Kind of, again, an odd way to word it, but there's one sign. Okay, it repeats again, starts repeating again right there, and we call that distance the wavelength. Stop sharing with you. And we'll move on to 8. Just a few more. Oop, that's 9. Sorry. Wow, don't I have 8? Maybe I don't have 8. I didn't. I must not have typed it in, or I typed over it if I did. Don't have a way for you to answer this one. What term is the phase? And the answer here, since I didn't give you a way to figure it out, that whole thing right there, kx plus or minus omega t, we refer to that as the phase. I'd have swore there was an 8th pole right there, but we're on to number 9 here. Any questions on that? That's phase. So the answer here would be C. Let's move to 9 and launch that. A little bit of math here. I tell you, I have to laugh a little bit. I encourage people to come see Max on Tuesday nights, because there are some people that don't know what the cosine of 90 or the sine of 90 or the sine of 180 or the cosine of 180. They just don't know those math facts. It makes it a little hard to teach torque when nobody knows what the sine of 90 or the sine of 180 is. It's a difficult thing. All right, waiting on one person here. Maximum. So I need this to be its maximum value. And a couple of you need to see Max on and Anna on Tuesday nights, because the way to make this a maximum is that this has to be 1, right? Everything I've underlined here. And the only way that could be 1 is if the phase is pi over 2, 90 degrees. Sine of pi over 2 is 1, multiplied by the amplitude gets you the maximum displacement. So right here, okay, kx minus omega t is equal to pi over 2. And our convention in physics is to stay in radians. I'll tell you, if you ever take an electrical engineering course, they'll go in degrees just because they can. All right, so pi over 2, that's where it's a maximum. All right, 10, 3 more of these, and then we'll be done, and we'll talk about something a little more exciting. And the maximum I'm talking about, that point right there, how fast does it go? speed of a wave, a traveling wave. That's funny, it's not showing me the bar graph. Almost in. All right, and you all got it. I don't know why we don't see the bar graph, but you can see 8 right there. So everybody got it. Yeah, any one of those works. I think the one people know the least is that one, okay, omega over K. But when you start doing quantum mechanics and electricity and magnetism, your upper level physics classes, okay, that's actually the one that's most important. This one to me makes sense. It's the distance the wave travels in one cycle divided by the time it takes to go through one cycle. So this one makes sense to me if I'm just thinking about velocity is a rate of change in time, okay? And then I realized that 1 over the period we call the frequency, and so that one shows up. But then how do I get omega over K? Well, if I can remember this one, I just multiply by 2 pi over 2 pi. And you can see right there, 2 pi over the period, that's omega, and 2 pi over the wavelength, well, that's K, and it's in the denominator. And so that's how that one shows up. And so that's how I've always remembered it. And maybe that'll help you here on one of these next questions. All right, let's go to that one. And we're up to 11 now. All right, one person we're waiting on. Everybody's in, everybody's right. And again, if you were having trouble thinking about it, remember that that phase has to have units of radians. And if you're an electrical engineer, of course, it's degrees. That has units of meters, right? And so you need to convert meters to radians. So you go 2 pi radians in every wavelength of distance in meters, and the meters for wavelength and the meters for x cancel, and sure enough, you're left with 2 pi. And then all you have to remember, I guess, is 2 pi radians is a cycle. If you're an engineer, electrical engineer, might be 360 divided by pi, and you somehow do it in degrees. Wacky engineers. Last one. All right, everybody's in. Almost got it right. And I may wonder, now this is omega, right? That's this term right here. Same function, has to take time in seconds and get it into radians. And so you need something that's in radians over a second. And so you go, well, there's 2 pi radians in every 1 period's worth of seconds. And so that works. 2 pi over t, 2 pi over the period. I should be careful not to just call it T, capital T, and that is the right answer. And so I found this funny that PowerPoint did this to me. I made A, B, C, D in Greek because, and I couldn't get it to change. And if you think that's wacky, well, so did I. I had no idea. All right, any questions on that? All right, that was kind of, the high schoolish stuff. Let's talk a little bit now about Fourier series. And here's kind of the point. Fourier says that if I take harmonics of some fundamental right there, harmonics, and notice not all of them necessarily, there's no twice the frequency, there's no 4 times the frequency, but I take harmonics, integer multiples of the fundamental of different of different amplitudes. The first one has just some normalized amplitude. Perhaps you want to think of that as just 1. Notice this one is 1/3 of that first amplitude. This one is 1/5. And you can kind of see the relationship in the pattern here. And that's what Fourier series is all about, finding that 1/3, 1/5, whatever the amplitude is compared to the first one. Okay, well, look what happens. If I take this guy and add them together, I get that. If I take this guy, and add them together, I get that. And if I take this guy, add the next one, and hopefully you can see the series pattern here. We jump right to infinity. What's 7 going to look like? Because 6 isn't there. This only has odd harmonics. 6 times the frequency should be, 7 times the frequency. The amplitude should be 1/7 of what the first one does. And if you keep doing that, you get a nice looking square wave. Okay, that's what Fourier said. And we can make all kinds of these. This is what I referred to as a periodic function. I can make any periodic function out of a series of harmonics of sines and cosines added together, but of just the right amplitude. All right, I'm going to stop sharing this with you. And we're going to zip over to, we lost somebody. 1, 2, 3, 4, 5, 6, 7. All right, I'm going to jump over. Somebody must be having internet trouble. Mine went down yesterday morning right before my lab. Go to a little panic right there. I'm going to show you a site, if I can find it. Google Chrome. What are you going to see here first? Hopefully not somebody's grades or something. Ooh, that's wrong one. So let's get over here. That was attendance for my lab. This is a website of a guy, he's an acoustician up at Penn State, guy by the name of Dan Russell. I always want to credit when I steal people's work. And what I'm showing here in Dan's animation is exactly what I just said. It goes a little fast, so I even have a way to slow it down here for you. But there was the first one, right? Omega 0. And then the next one that was, see, 3, 5, 7, only the odd harmonics. It adds the third one, which is 1/3 the amplitude, takes the 5th one, which is 1/5 the amplitude, the 7th one, which is 1/7, and he very quickly adds these up, and you can see how it goes from just being a sine wave, and as you add these up, it becomes looking more and more like that square wave I was talking about. You can do the same thing for a triangle wave. You can do the same thing for a sawtooth. This is my favorite because this is the one that's most relevant to modern physics. If I just add up a bunch of equal amplitudes, notice I get a pulse out of that. And that's fairly profound for modern physics and quantum mechanics. And we'll revisit that again on Monday, but that's the one we want to hang on to. I have another guy's work I steal regularly. This is an applet written by a guy named Falstad. I don't know where he teaches, but his stuff is remarkable in terms of being able to put things together. And we're going to work this problem here in a second, so I'll come back to it. We're going to do the math for this. I want to go to that square wave we were talking about before, and you can see how nicely it gets put together. I'm going to clear it, and then I'm going to go through what I just said. Okay, so it's only the odd harmonics. So there's the first one, okay? And when I put my finger, my mouse over, you can see there it is. There's no second one. Then I have the third one, which is about 1/3 of the amplitude of the one before it. And you see it right there, 1/3 of the amplitude of the previous one. And you can see what it does right here. It kind of flattens it out a little bit. I don't have a 4th one, but then I have a 5th one, okay? And it's supposed to be about 1/5 of the original, right? So there's the original, the fundamental, there's the 3rd harmonic, there's the 5th harmonic, and you can see what's happening here. Doesn't have a 6. Now I'll go to the 7th, and I'm trying to estimate the 7th. Okay, there's the 7th. No 8th. Go to the 9th, And you can see it's starting to flatten out quite nicely for me. Okay. And of course, this guy Falstead, he's put it together. He gets to use a bigger first one than I got to, but you get these little wings at the end, but it gets pretty flat right here. These are called the Arceval wings. It's a mathematical artifact to ask a calculus teacher about. That's obviously just a mathematical artifact. If you actually could go to infinity, those would go away. But I don't know how many we got here. What, about 20, 25 maybe different sine waves? What's this one right here? It's not labeled. Oh, that's the 47th, isn't it? 47, 48. And so I'm not even doing 50 of these. If you went to infinity, these little guys would go away. All right, I'm going to show you two things now. First of all, where do you calculate the amplitudes that are necessary to build these structures, build these periodic waveforms? And just a couple of them. There's a sawtooth I mentioned. You can see what signs went into that. Kind of interesting. You use every one, but some of the amplitudes become negative, right? That one's the positive one, and then you got a negative one, and then a positive one, and the relative amplitude is the key to building these structures. So how do you get those amplitudes? And the one we're going to do as a problem, where is it? Where to go? Squared, sawtooth, triangle. That one. We're going to do that one. Okay. And interesting, I built my periodic structures with sines. I didn't show this to you, but you can also use cosines. You can use either one. In fact, Fourier said it could be either, depending on what you're doing. And there's some rules on that. Okay. But I want to work a problem. So I'm going to jump out of this, and I'm going to show you the worksheet problem for today. And then I'm going to work through one of them, and then I'll leave you for some others. All right, so I want to go to that, share that. We'll come back to that. Here's the worksheet problem. And I give you what a mathematician may or may not have shown you. It's an integral calculus problem. So presumably your calculus teacher could have showed you this in calculus 2, okay? And this top line here is a statement of Fourier's theorem mathematically. Fourier says that any function at all that's periodic here, that's the limit on that thing. It has to be periodic, can be made by a sum of cosines and sines, and it's traditional to write it in that order, of varying amplitude. So you got to figure out what the amplitudes are. And if this looks a little weird, just remember that 2 pi over lambda, and that what we just called K. And that's why I wrote it right here, right? So it's really N times K times X, N times K times X. That's what you got right there. And so the trick, of course, is N represents the harmonics, figuring out what these A's and B's are. And according to Fourier, and I'll show you why here in just a second, if you're looking for the A coefficients, you just have to do that integral with that constant out front. If you're looking for the B coefficients, you got to be able to do that integral. And the thing to pay attention to is N right here tells you which coefficient you're finding. The first one, the third one, the seventh one, whatever it is. If you happen to get even numbered ones that don't go to 0, that could be great too, okay? There is one thing here that is subtle, and I'll hopefully show it to you. There is what I would call a constant term, A0. And just as a question will come up, is there a B0? Okay, is there a B0? And hopefully you can see that there isn't. Look, if N is equal to 0 right here, cosine is 0, 1. If N is equal to 0 right here, which would be the B0 term, well, the sine is 0, so there is no B0 term. There's only an A0 term, and that's the integral you got to do to find that. And so some people will go, well, take the sum from 1. And by the way, I guess there is an implied set of parentheses on both the terms. Some people say go from 1 and just add on A0 if you want, okay? And this is sometimes called the DC term, the constant, all right? So anyway, where does that come from? And what are we going to do with it? Let's see if I can get back to a pointer. There we go. I should be able to scroll down, and I'll clear my junk here. Clear my drawings. Here's the problem we want to do. We want to figure out, and I think all we need to do is get the cosine coefficients A for this guy. I want to be able to figure out what the amplitudes all are to create this triangle wave. The example, I just showed you a picture of it over on Fallstat's website simulation. And there's the answers. So I'll know when I get it right, because those are the answers. I've done this problem before. I'll even show you a little bit in Excel, if I got the time here, about, let's see, let's put them together, just like the animations do. No kidding, I'll calculate them for you in Excel, each of the waves, and we'll add them together and we'll see if, no kidding, they look like this. Now, why did I only use the cosines for this particular problem? Well, if you think about it, cosine is an even function. Everybody know what I mean by even? Even means that if I look, let me go back to my drawing tool here. If I draw a cosine, and I'll draw it right here, and that's a lousy looking cosine. But if I go out some positive angle and some negative angle, and if I drawn it nice and symmetric, I should have the same value, right? For the positive and the negative angle. That makes it even. On the other hand, sine doesn't look like that. If I go out some positive angle on sine, well, it's the same number, it's just negative if I go on the negative angle. We call that an odd function, odd and even. Parabolas are generally odd, right? I'm sorry, parabolas are generally even. Cubic functions are odd. And you can kind of see why, right? That's where the name comes from. If there's an even exponent, it's an even function. It'll be symmetric. If it's a quad, if it's an odd, like a cubic, or what's the next one? Quintic. I don't even know what the right word is. X to the fifth power. It's an odd function, and that's where the name comes from. If you look at my at the example problem we're working here, this is even. So the only way I could add up, and if you picture it in the animation, the simulation I did, the only way I can get a bunch of things to add up to give me this is if I use cosines. If I try to use sine, that's an odd function. How am I going to construct this thing out of odds? I would need something to be negative, and it's not. Okay, so that saves your work very often in a problem like this. All I got to do is look for the cosine coefficients, including A0, because it exists. All right, so let me shift over a little bit to why those equations are true, and then we'll work the problem. And why the equations are true is, to some degree, the domain of what a calculus teacher should tell you, because an integral calculus teacher has to teach you something about sine and cosine orthogonality relationships. It's a mouthful of a word, orthogonality, but it just means this. If I integrate a sine times a cosine, I don't care which harmonic of the sine and which harmonic of the cosine, it integrates to zero every time. There's probably an elegant mathematical proof of that someplace that I just don't care about, but it's true, and I've learned it as a rule. Sine times a cosine is always zero. If I look at a sine times a sine, which I'm integrating, and by the way, the integration limits are just over one repeat cycle, one wavelength, and I'm integrating over X. You can do this in the time domain, as people would say, integrating over time and go over one period, and then you'd have omega, but we're doing space today, but you'll see people do it with replacing time for X. But anyway, if I look at sine times a sine integrated here, and they're differing harmonics, well, if the harmonics are different, the answer is zero. And that's where the word comes from. We say those two sines are orthogonal, just like we say a sine and a cosine are orthogonal, okay? Whereas if n is equal to m, okay, that just becomes sine squared, right? And the answer is, it's like a lookup. Go to an integral table, it's lambda over 2, okay? Because you integrated up from 0 to lambda. All right, and there is one special case, I guess, if m and n are both 0, well, then it's 0, I guess, as well, okay? And that's why, I guess, that's the one that tells you there is no B0 coefficient, if you want to be firm and mathematical about that. Look at cosine, same kind of deal. If m and n, the harmonics aren't the same harmonic, these two guys integrate to 0. If they are the same, it integrates to lambda over 2. And this is a special case for the cosine. If m and n are both 0, well, it integrates to lambda. And that's why there is an A0 term technically. All right, that has to be the background mathematics for Fourier's theorem, because then where did Fourier get his results? Something people refer to as Fourier's trick. Sometimes I've heard it referred to as Fourier's hammer, because this is how you hammer out those coefficients, A and B here. And again, I do worry about notation. There is an implied set of parentheses. The sum is over both the sine and the cosine terms. And if you hate the notation, if you're not comfortable with it because you just haven't worked with these sigma summation signs, the Riemann sums, all that enough time, I took the trouble to write them out for you. Okay, this first term right here, right, A0, A1, notice 1, 1, right, N, 2, 2, 3, 3. And remember, I said there is no B0. There's no B equals 0 term because of the fact that sine of 0 is 0. But 1, 1. Now I'm writing out this guy, and I just wrote out the first 3. And of course, there's more. There's an infinite number of both. And so here's what Fourier said in his trick. Fourier said, okay, what if I want to find A2? What do I do? And the answer goes like this. The first thing you do, I got to switch over to pointer. That's just annoying as all get out. And then I got to, we'll leave that right now. I'm not quite gonna be able to get them both. So let me clear my marks. The first thing you do if I want A2, okay, and that was the second of the A's, right, is I got to multiply everything by cosine of 2kx, okay? See, I want, come on, give me a drawing tool back. Yeah, I got a drawing tool back. I got to multiply, if I want A2, I multiply everything by cosine of 2kx. And so I did that, okay? Multiply by cosine of 2kx, multiply by cosine of 2kx, multiply by cosine of 2kx of every term. Oh, come back. Every term of the previous series right there, I multiplied everything by 2kx. All right, great, done. Clear all your drawings. And orthogonality says, well, that one's 0. 1, 2, 0. That one's not 0. That's why I multiplied by cosine of 2kx, because that one that has the coefficient A2 that I'm looking for, that doesn't integrate to 0 by orthogonality. That one does, 3, 2. And then every other one, 4, 2, 5, 2, 6, 2, every other term in the sum, except for this one right here, integrates to 0 by orthogonality. And every B coefficient, well, that integral that it's associated with integrates to 0 as well. So I multiplied by cosine of 2kx, and then I integrated and used orthogonality rules. And look what happens to the series. It collapses just down to one term. Okay, kind of cool. It makes things quick. That's the trick that Fourier realized back in the 1800s. Okay, well, let's see. I'll just write things that aren't 0. The thing that was on the left right here, I'm writing it over again. And then the one term that didn't go to 0, well, it's A2. And I used the orthogonality case of m equal to m. It was just lambda over 2, right? And so now solve for A2, bring the 2 over lambda to the other side of the equation, multiply it by this stuff. A2 is 2 over lambda, integrate from 0 to lambda of the function times cosine of 2 times k times x integrated over x. I'm going to generalize. What if I wasn't looking for 2? What if I was looking for any value n? Well, that and that would just become n's. Okay, great. And what would the b's look like? Had I been looking for any of the b's, I would have multiplied by sine of nkx and turned exactly the same trick, okay, and worked it exactly the same way. Okay, so those are the way those are Fourier coefficients. That's how you calculate them. I did talk about 0. What if it was 0? What if n was equal to 0? Because remember, there is none for sine. There's only one for the cosine, so there's only an A0. Well, I would do exactly the same thing. I would get the m equals n equals 0 special case. The integral on this side would have been lambda. Cosine of 0 is just 1, and so that's how you find the A0 coefficients, right? And that's why I wrote those things. These two equations, and the third one right there for A0, are exactly what came out of Fourier's trick. All right, so now we want to do this guy. We want to do this periodic structure right here. I want to come up with what are the coefficients in this series that make that thing up. And so let's do that problem here real quick. And let's see, my example is this triangle wave. And so I drew it right here, just drew a couple of the cycles. And the hard part about this is you got to figure out what f of x is, don't you? And I guess you also have to know what a wavelength is. And so let's see if I can point that out. What is the repeat interval lambda? Well, I think the thing repeats right there. Okay, I could have used here to here from 0 to 2a if I wanted to, but I think that tells me that the wavelength, the repeat interval here is 2a. This is where people get kind of have mistaken ideas. What is the wavelength? Because remember, you're integrating from 0 to 1 wavelength. So if I could go from 0 to 2a. I chose this interval right here for one simple reason. It's easier to write the equation for this guy and this guy than it is to write the equation for this guy and that guy. But either one would have worked. And so what I did is I said, well, the intercept is whatever the height was, which we're calling h here. And then the slope is h over a, and it's positive right here from minus a to 0. And it's negative right here from 0 to a. And it just looked easier to do for me to get those two values of f of x. If I'd have tried to write an equation for this, I would have had to work back to figure out what the y-intercept is. I mean, they're straight lines, so y is equal to mx plus b is the process by which I figure out what the function is, okay? But it would have been harder to get this one, and that's why I stayed with this. And that's just experience talking right there. There would have been nothing wrong with taking 0 to a and then writing another equation for the next segment from a to 2a and integrating from 0 to 2a overall. Now, by virtue of the choice I made, I had to break up the Fourier integral, right? Let's make sure it's clear what I'm doing. I'm working this right here, right? A sub n is equal to, and I'm supposed to integrate over one wavelength, but f of x here is multi-valued. It has one equation from minus a to 0. It has a different value, a different equation from 0 to a. And because of that, I had to break that integral up into two pieces. From minus a to 0, that's what the value of f of x is. And from 0 to a, that's what the value of x is. Now, look, I guess I'm doing a0 first, okay? We'll do a sub n next, but that's the idea. And so I just work through the integral. You can check my math if you don't like it. I just made 4 integrals, 1, 2, 3, 4 out of these 2 integrals, and I evaluated them one at a time, and I very carefully applied the limits. And when I'm done, I get the fact that a0 is h over 2. All right, great. Now let's get a sub n, exactly the same thing, except now there's my function over the range minus a to 0. There's my function over the range 0 to a, all right? I could have put this in Wolfram alpha. I decided to take the macho approach and literally expand the first integral. Then there's a second one. Then there's the third one. Then there's the fourth one. I wrote them all out. I realized these two guys, you're integrating a cosine over I guess half of a repeat cycle. Those two integrated to 0, and I just looked those two up, I guess. No, I actually did them, I think. Integral a cosine of kx dx, and the integral right there, those were the answers. Actually, no, I looked those up, or I put them into Wolfram alpha. I forget how I actually did that. Any event, I combine those two, and I get this relationship is the answer. All right, and then I said, well, what's n? N could be any integer, right? Well, if I put n equals 1, cosine of pi, that's -1, -1, that's -2. Good to go there. And what about when n is equal to 2? When n is equal to 2, this is 1 minus 1, which is 0. What about n equals 3? Minus 1, that's minus 2. Okay, so that one's not 0, but now I've got 2 squared there. So I got, I'm sorry, 3 squared. What am I doing here now? I just did 2. When I do 1, I get this. 2 becomes 0, 1 minus 1. 3 becomes 3 pi minus 1. That's minus 1 minus 1. And then I've got 3 squared right there. So that's the third one over here. And you can see 4 would also be 0, right? Because it'd be 1 minus 1. 5 would be non-zero. That's why the odd ones persist and the even amplitudes go away, huh? And so that's my result. That's what I think the answer is. I just simplified this. It's 4 times h. That should be, where did 2 times h? Yeah, I worry about what I wrote right there. I worry about that. I believe the n squared pi squared, and I believe the 4. I'm not sure I believe the pi. What should that be? That should be h, right? Mistake right there. That should be h. All right, any event, I could go through the b's, but I fully expected the b coefficients to be 0 because this is an even function. Signs are odd. Our triangle wave is symmetric. All right, in just a few minutes that's left here, I want to show you an Excel spreadsheet where I added these up just to prove to you that they do indeed add up to give me that function that I was talking about. All right, so share screen, go to Excel, and here's how I set it up. I took n and found each of those coefficients. I only needed the odd ones, so I actually got numeric values all the way up to 13. I didn't use all of them. I only used the first 3, and I got a pretty good wave, okay? And then right here, there's my h over 2, okay? Then I found the first one. I don't know why I have a column B there. There's A1. If you look, see, there's a 1 times pi times A15, that guy. All right. And I guess that would be, yeah, okay. That would be a good thing, because then I've got the first term. And there it is. There's A1 being graphed. So this entire column is graphed right there. Okay. I added it to the A0 term. And when I added the A0 term, which was h over 2 plus the first term right here, A1, you can see it just shifted it up, right? This one, there's the origin. The origin is down here, so it shifted it up. There's the A3 term, okay, right there. You can see it's 1/3 the amplitude. I took that one and added it up, and all of a sudden it's starting to look like a triangle wave. And then I took the 5th one, okay. There's the 5th one. You could see it's 1/5 the amplitude. I took h over 2, which is the A0 term, plus A1, plus A3, plus A5, and it's starting to look like a pretty good triangle just with 3 terms. If I did an infinite number of terms, sure enough, it would work. All right, that's for A series in a nutshell. Now, I want to make a point here, and then we'll have to go, and we'll save the worksheet for Monday. So stop sharing that. And we got to get back to my PowerPoint, which has gone away. Let's put some of this away so that the PowerPoint can restore itself. All right, it's still there. Let's cancel that and let's share it again. There it is. Now it's present. It wasn't there on the possible things to share. All right, so I guess the big wave I want to talk about, because it's important to what we're doing right here, is this one. Because what if I do a addition of all these things, I get a wave packet, okay? Let's simplify that out even just a little bit. Let's look Where did I put it? Where did I put it? Where did I put it? Bup, 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 bup. Sorry about this. There it is. I can't see that. She made the little guide around the side. Let's just add 2 waves up. Slightly different frequency, right? And I went through the math of this in the pre-lecture video, but if I add these 2 guys up, I need a trig identity. Okay, there is one. And it's just the difference over 2, sum over 2. And when I rearrange those things, okay, I go, that's delta omega, that's delta K, put that right here. This becomes just an average K and an average omega right there. And so what does this look like? Well, I think it looks like this piece right here. In fact, that thing is this dashed line right there, okay? And this thing is the sine wave. We say that this guy right here is the envelope, and this guy right here is the carrier, right? And let me very quickly show you an animation. I'm 2 minutes over here, that demonstrates what I'm showing here. Stop sharing this, go back to Falstead's stuff. Where are we? Google Chrome, yep, share that. Go to Falstead. And no, I want to go back. There we go, dispersion applet. As soon as you see this, we're done. All right, so I want to take the frequency of just 2 waves, like I was just looking at, and let's slow down the simulation so you can see it. And hopefully you see I've just added 2 waves of slightly different frequency. Let's slow them down a little bit. And you can see I get these packets. Speed it up a little bit. And you can see that the carrier, the sine wave itself, is moving at 1 speed, and the packet is moving at another speed. We refer to those 2 speeds as the phase velocity for the carrier. That's the average of these 2 velocities right here, okay? And then the packet itself is moving at a different speed. And let me make some examples here. If you look on this one, I think the carrier is moving to the right, but I'm not sure what direction the packet is moving. See, I kind of put them together there. Now the packet is also moving to the right, and the carrier is moving to the right. See, the packet is moving. Now let's change the speed of the first one, and now I can make the packet go to the left and the carrier go to the right. So it seems the packet and the carrier can move at different speeds. They can even move, heck, in different directions, right? And so as we model, according to de Broglie, things, electrons, protons, you, me, BBs, bullets, as we model them as waves, as de Broglie said, which part of the wave? If this packet here represents a particle, how fast is it going? Is it moving at the packet speed, or is it moving at the speed of the carrier, which we call the phase speed? That's the question. And I think we'll pick that up on Monday. I have an example. We'll start off right away with the worksheet where you'll do some calculations on that. And then we'll make a conclusion. If a wave is being modeled, if a particle is being modeled as a wave, and it might be a packet like this, which speed is it traveling at? The speed of the carrier or the speed of the packet? I'll let you mull that over the weekend. Sorry for going long here. I think this kind of marks a turning point in the course. We've been thinking about phenomena, and now the course will get a little bit more mathematical. And so I'll be talking a little bit more about things in class, more of a conventional lecture than we've been doing in the past. All right, I'm going to stop sharing with you. No worksheet over the weekend. There is new homework up for Wednesday if you feel like you want to be busy. Otherwise, have a great weekend. Any questions for me? I know it's a lot in one day, a lot to pack in for waves, But if you got nothing, I'll hang around.
Will that be posted on online?
Which one? What we did today?
Yeah.
Yeah, I record it. It'll be at the very bottom of our canvas on the class videos.
Awesome. Thank you.
You bet. And of course, there was a pre-lecture video as well, and that, you know, some of the more fundamental stuff where we talked about the packets and the speeds that they travel at. All right. Dangerous stuff. Absolutely, I agree. Yeah, we're going to see some high power math between now and the last third of the semester. All right, think about it over the weekend. Make a decision. What's the particle? Which speed does the particle move at? The packet or the carrier? All right, we'll see you next time. Have a great weekend.
Okay, thank you. You too.
And I'm going to stop recording.